And then they have refined it time to time. And there's so every few years they refine it. So they have been doing this for revise every 7 to 10 years. And so there's a current version, which I forget what it is, E or F something. And there's also there is a computational procedure proposed by Bell-Core, and it is called Bell-Core model. And now, why do people use hardware? How accurate are the results? Remember, these are statistical results, and so nobody can guarantee that this thing, which is supposed to fail after 5 years, will fail exactly after 5 years, and on one day after 5 years, it would have find it broken.
Because in hardware, it really depends on the environment and the way hardware is used, I guess.
Yeah, that is true.
Yeah.
So they used a number of things, and for example, the state of technology and the complexity of the IC, for example. More complex the IC is, higher would be the failure rate. And they come up with some kind of empirical relationship that uses the number of components on a chip and the number of pins of a chip, and they empirically correlate it with the failure rate, and of course that changes with technology. So these methods are available in the literature and they are used. And there's no guarantee that the results would be accurate, but they're excellent for comparison. You want to compare two designs, then you can compare two designs. And even if the estimates are off, even if the methods are not exactly accurate, it is still good for comparison. And you can do reliability and performance trade-off, or you can do reliability versus cost trade-off. If you have some analytical methods, you can optimize your design. You can identify reliability weak spots. So you can find out that this particular unit causes most of the failures, is likely to cause most of the failures, then you can improve on, you can focus on that. You can track reliability improvement. So the methods are well known, well established in hardware, but not quite as well established in software. Or at least they were not that well established maybe 15 years ago, 20 years ago, and now they have been around for a while, so people are more willing to accept them. Now, if you compare software and hardware defects, there are some differences. Most of the hardware defects, they arise in the field. Something has been shipped, it has been working, and then something goes wrong and it breaks. Whereas in case of software, defects are typically encountered during testing. What happens in software is that so in software the faults are man-made. Actually, that's also true for hardware. So in hardware, when you first design it, typically you go through some design verification thing, which is very similar to software testing. Basically, you have a man-made design, which is the hardware description of a piece of hardware, and you examine that description, and that is very similar to what we do with software. So there is a phase which is called reliability growth. So here you have the debugging effort. Let us say that you are developing some software and it is currently under testing, you have not released it. Then the failure rate should go down with debugging. So this is your failure rate. And this is referred to as reliability growth, because your failure rate is going down because you're removing the bugs and your software is getting better. Now what happens when you release a software? Let's say you ship it out and you're not going to make any changes in it. And if you didn't make any changes, then things would be like this. Your failure rate is going to be like this. Assuming, this is the case when you have no bug removal. If you buy a piece of software and you never update it, then it will have a sort of a constant failure rate because you're not removing any bugs. However, things become more complex as software evolves because you have successive versions, patches. So what will happen if a new feature is added, when you add a new feature, you will inject some more bugs in it. So actually the failure rate will actually go up for a little bit because you have added some new feature in it. But then the failure rate will go down if they keep on fixing it. Now what is now let's look at a comparison of the methods used in hardware and software reliability. Now we are going to be talking about models that allow you to estimate something. Now how do you do the model selection? Model selection in case of hardware were based on past experience with similar units. Past experience with similar units. For example, you want to find out failure rate of memory chips. You take some memory chips, examine them, or if you had examined some similar memory chips which were not exactly identical, somehow you will try to translate using some kind of empirical approach. But anyway, past experience with similar units. For hardware, software, the model selection would be based on past experience with similar units. So you have done, within your organization, you have in the past have some experience, you have done some modeling, let us say for reliability growth, and it has worked well in the past. You can assume that it will work probably well as long as your process is still similar. Now there are two things. You need to select the model that you're going to apply, and you need to estimate the parameters that go into those models. Parameters estimated. Using, now how do you estimate parameters? For example, failure rate of memory chips. Well, past experience with similar units, right? Past experience okay, now what about for software? How do you estimate the parameters? Well, you could still do the same thing. In the early part of testing, you could use past experience with similar units. You could rely on past experience. However, as you keep testing, what will happen? You already have some data which is coming from the very same product that you are working with. So with software, you could have some data from the unit under test. So you have some data which is coming from the very same device which you are testing, and that makes it better for software reliability, because you can base your judgment based on what you have found for the very same product. So potentially you can do much better with software reliability evaluation than you can with hardware. Okay, now let's look at some basic definitions. Okay, so let's look at some definitions of software reliability. Okay, what are the most common measures of software reliability? Let's look at some basic definitions. Okay, one thing that could possibly be defined in different ways, and let me define it briefly. A defect is something that requires a corrective action. So you encounter some problem, and that problem may require you to fix a single statement, or it might require you to fix maybe a few statements, but you count that as one fault. There's a term defect density. Now, defect density is a normalized measure, and typically defect density is measured in terms of defects per 1,000 lines of code. But let's see. And obviously, you don't want to count comments there, because so let's exclude comments, non-comment. And okay, so are we talking about source lines of code or object? So it's source lines of code always, well, in most cases. Source lines. And the common abbreviation is, this is non-comment. LOC is the number of lines of code. Now there are some tools available that will allow you to count the number of lines of code. So what are those tools called?
Well, I forgot the name, but there are two kinds of things.
Yes, if you need a package to count number of lines of code, so you know some, right?
Yes, sir.
So because he has been counting. So actually, to count the number of lines of code, it takes a lot of work, especially if it's a big package. Fortunately, there are some nice tools available, and some of them are free.
It's free.
So, which he has been using for some of his work. Okay, so that's defect density. Now I will give you some. And then there is failure intensity. Failure intensity is the rate at which failures are encountered during execution. And then there is mean time to failure. And in this case, it is inverse of failure intensity. Now incidentally, when I say mean time to failure, there is a little bit of difference